As far as power reduction in BIST is concerned, so another possibility is to partition the circuit. For example, if suppose we have a circuit which has got inputs A, B, C, D, and there are two outputs E and F. Now, it may be possible to divide the circuit into two parts, circuit 1 and circuit 2. Okay. So, there will be naturally, since they are part of one circuit, so there will be lines running between the two circuits, like some signals from circuit 1 will go to circuit 2, something from circuit 2 will come to circuit 1. But if it is done, then suppose we are trying to test this circuit 1. So, when we are trying to test this circuit 1, so we put a number of multiplexers. It may be the case that this input B is common to both circuit 1 and circuit 2. So, what we do, we set this multiplexer in such a fashion that when we are testing circuit 1, so this B input comes to this one, whereas this input is not reaching there. So, this is basically some 0 or some previous value, whatever it is, depends on the whether it is a latched input or some gated input, something like that. So, it will remain at as the same value at circuit 2. So, this comes to the B input comes to circuit 1. Similarly, it may be common that C input is there for both circuit 1 and circuit 2. So, C input is obtained from this input. So, this line is not shown explicitly from C to this. So, this may be coming to circuit 1 via configuration of these multiplexers. So, that way this A, B, C. So, these are the three inputs given to circuit 1. Now, we can see that some other inputs which are common between some other signal lines which are common between circuit 1 and circuit 2 may be programmed to reach circuit 2 when we will be testing circuit 2. So, by setting these multiplexers properly, so we can partition the circuit into circuit 1 and circuit 2, and we can test them separately. So, when we are testing circuit 1, so these multiplexers are set in such a fashion that these A, B, C inputs and the lines from circuit 2. So, they come to circuit 1. Similarly, the other way, that is when you are testing circuit 2, the other thing happens. Similarly, the E and F are two outputs. So, it may be that this output of circuit 2 that is coming here. So, that may be redirected to E. So, this of course depends on the detailed circuit that we have. This is just an example. So, if we do that, then this circuit will be partitioned. Now, we can have BIST which will be of lesser the test pattern generator for BIST will be of lesser width, and so we have got this you know that if I have got an n input circuit. So, in ideal case I will require an n bit LFSR to generate the test patterns. Now, if I reduce this n to some other value, say n by 2, then 2 power n by 2 plus 2 power n by 2. So, many patterns will be needed for testing the two circuits separately. Of course, some patterns will be needed to test the multiplexers as well, but the total sum will be much less than 2 power n. So, that way this circuit partitioning can reduce test time, and since the circuit 2 is not excited when circuit 1 is being tested, circuit 2 can be totally in a non excited mode, inputs are not modified there. So, it can it will consume very little power, maybe only the leakage power part will be consumed, but no dynamic power will be consumed. So, that way power reduction can be achieved. Another way of testing the circuits is via external testing. So, when we have got the test equipment coming separately. So, these test patterns are stored in the memory of the ATE, and then this circuit that we are going to test. So, they are so the scan flip flops of the circuit, they form a chain, scan chain, and it is also assumed that this circuit has got some primary inputs also, but primary inputs are also assumed to be connected over a scan chain. So, it is in this case it is taken as the full circuit, all the inputs are coming through the scan flip flops. Now, from the ATE channel, the bits will be shifted through this scan flip flops, the test pattern bits will be shifted through this scan flip flop, and the response bits. So, they will be collected again onto the scan chain flip flops, and they will be shifted out through this ATE channel. So, this is the method for external testing that we have seen in previous classes. Now, there can be several techniques by which we can do this external testing in a low power manner. So, we can have some ATPG algorithms that target low power. So, it will try to generate test patterns so that power consumption is less. Then there are some ordering techniques. So, we can change the order of these test patterns to be applied to reduce the circuit transitions. Then we can go for some scan power minimization. So, scan power minimization, it can talk about test vector ordering, scan flip flop ordering. Then we can control the inputs, we can do some vector compaction, can take help of test data compression. Then another possibility is the best primary input change time. So, what it tells is that we have got this any test pattern has got one part which is primary input, the other part constitutes the pseudo primary input. So, the pseudo primary input part is actually shifted through the scan chain. Now, since that shifting will take time, so when exactly we are going to change the primary input part, so that may determine the power consumption, the transitions in the circuit. Then there are lot of scan chain transformation techniques like scan flip flop ordering, then modifying the flip flop types like from T to D, or using both Q and Q bar outputs of the scan flip flops. Then we can put some XOR gates into the scan chain at some selected positions, and also we can go for multiple scan chain. So, we will look into some of these strategies. Low power ATPG. So, low power ATPG, so any standard ATPG algorithm, so that will leave a number of don't cares unfair not filled. So, actually those don't cares can be exploited so that we can minimize the transitions in a circuit. So, what I want to mean is, if this is the circuit, okay. So, this test pattern generator has given me two test vectors, say T1 and T2. So, first T1 will be applied to the circuit and then T2 will be applied to the circuit. Now, if we can ensure that between T1 and T2 many bits are not changing. So, if many bits are not changing, then it is possible that the many of the gates which are getting input from the primary input of this from the primary input will not do a transition, and subsequently the gates at successive stages, they will also not make much transition if the first level gates are not doing transition. Now, we have told previously that in a test pattern generation process that successive test patterns are highly uncorrelated, that is the number of similarity bits between two test pattern is generally very low to make sure that new faults are being excited. But it may so happen that though they are different, but many of the bits may be don't cares in one of the patterns. So, T1 may be something like say 1 x 0 1 and T2 may be x 1, then this is say 1 and this is say 1. So, there are changes, but you see that there. So, if I fill this x by 1 and fill this x by 1, then the Hamming distance between the patterns can reduce compared to the case where these x's will be filled up randomly. So, what we can do, this any ATPG algorithm, it can have a post processing stage in which the don't cares bit don't care bits will be filled up judiciously, so that number of transitions between two successive test vectors get minimized. So, this is one possibility. Then generating redundant set of patterns. So, what it says is that you know that we sometimes in our class we have discussed that n detect test pattern set. So, n detect means a fault is not dropped from the set of faults to be considered by the ATPG algorithm as soon as it gets detected by a single pattern. Rather, it is kept in the fault list till it has been detected n times. So, n may be typically equal to 2 or 3, but so what we get is for every fault we are getting a number of patterns. So, this is in this way we can generate a redundant set of patterns. Now, most of the ATPG algorithms, when you generate this n detect pattern set, it does not do any compaction of the test set. So, for every fault I get say n equal to 2, so 2 patterns. So, if there are say k number of faults in the circuit, then I get a total of 2k number of patterns. So, there is no compaction that is done. So, what will happen is that, so many of these patterns, they have the capability to detect number of faults. So, though it has been taken into the set because it could detect one particular fault, but it is they have the potential to detect more number of faults. So, once we have got a redundant set of patterns, so we can do something so that we can choose patterns so that they consume less power. So, a number of patterns are generated for each fault depending upon that n detect principle. For sequential circuit testing, patterns are to be applied in a sequence only. For sequential circuit, though we did not discuss about sequential ATPG in general, but what happens in that case is the first pattern or a set of patterns will take the circuit to a particular state, and then the final pattern it will actually excite the fault. So, that way there is a sequence of patterns that that are present, which will be doing the test excitation and observation. So, sequential circuit patterns are to be applied in a sequence only, and each such sequence may have different power requirements. So, for the same fault I may get different sequences of test patterns. So, which sequence we pick up, so that there may be option. Okay. So, maybe some sequence apparently seems to be longer than some other sequence, but it may so happen that the second sequence between the successive patterns Hamming distance is low. As a result, they do not create lot of transitions in the circuit inputs. So, lot of gates do not switch. So, that way power consumption may be low. So, we can go for the sequence which may be longer, but power values are low. So, if we select these sequences requiring less power, so fault coverage is not sacrificed, because for every fault I have got options of sequences, and for I am including at least one sequence for each fault. So, fault coverage is not dropped, but our power consumption may be reduced. For combinational circuits, the situation is slightly more difficult as far as power consumption is concerned. First of all, the first few steps are same, like we generate a set of redundant patterns. So, for every fault we generate n number of patterns, then we do a fault simulation. So, after fault simulation we can see that every pattern, suppose we have generated a redundant set of patterns consisting of say T1, T2, T3 up to T100, where T1 is targeting fault F1, T2 is targeting fault F2, like that T100 is targeting fault F100. Now, after this it passes through a fault simulation stage, and after doing fault simulation we may find that T1 detects a number of faults F1, F10, F15 and F20. Though originally the ATPG tool it had generated it targeted to F1 only. So, this way for every fault we see a set of faults, every pattern we see a set of faults that pattern can detect. So, identify the faults detected by each of them. So, that is basically via fault simulation, and we compute number of gate transitions for each pair of test vectors. Now, what will happen is that since this is a combinational circuit, so to detect a fault it is sufficient just to apply the corresponding pattern. It is not dependent like what was the previous pattern that was applied, particularly if we are targeting staccato faults. So, this is particularly true. For delay fault it is slightly different, because delay fault is a 2 pattern test. So, there I have to consider groups of 2 patterns. Okay. But if we are restricting to say staccato fault, which covers most of the other faults as well, the test pattern generated by staccato fault covers most of the other faults as well. So, we can see that suppose we first apply T1, now I have a choice. So, I can apply T2, I can apply T3, I can apply T4, I can apply T100, it does not matter. So, somebody applying patterns in this sequence T1, T2, T100, and another person applying it in this sequence T1, T100, then T2, then T10, then finally say T2 sorry T3 at the end. So, these two, so if all the patterns are applied to a combinational circuit, the fault coverage will remain unaltered. So, we can compute what are the so we compute this type of transitions, like first T1 followed by T2. So, when T1 is applied, circuit gates are at some values. After that, if I apply T2, some of the gates will do transition. So, we count how many transitions are occurring if I apply T2 after T1. Similarly, T1 followed by T3. So, this way up to T1 followed by T100. Then we do T2 followed by T1, T2 followed by T3. So, this way if we compute all these pairs of vectors, all these pairs of test patterns, and see what are the transitions that are occurring if I first apply the first pattern and followed by the second pattern. So, this way it computes the number of gate transitions for each pair of test vectors. Then we perform a search for a pattern set with low power and high fault coverage with a proper reordering of the set. Now now I have a choice. Suppose it says that T1 followed by T2, it consumes power P1. So, in terms of gate transitions, maybe it is now P1 number of gates do transition. So, then this may be P2. So, like that I have got a number of for each test pattern pair, I have got the number of transitions that are occurring in the circuit, and number of transitions, you know, that is an indicator of the dynamic power consumption of the circuit if the patterns are applied in that sequence. Now, from this we can take whichever pair is consuming the minimum power. Suppose the pair T50 T60 that takes the minimum power. So, we start the with a test pattern set, first T50 then T60. Now, once we have chosen T50 T60 pair, so we have got certain faults already detected by from this table. We will know what are the faults that are covered by this T50 T60 pair. So, those faults I can drop from my consideration. Okay. Then from the remaining pattern set, I can find out after T60 which pattern combination can give me the next best power consumption. Maybe if the T60 T40 pair gives the next minimum power consumption. So, we will take up T60 T40, or rather we will apply T40 after this, provided T40 identifies a good number of new faults which are not covered by T50 and T60. So, this way we can have some sort of we can search for a pattern set with low power and high fault coverage. So, there will be two cost function component, one is the power consumption and the other is the fault coverage. So, if we do not do a fault coverage analysis, then of course, it will select patterns which consume pattern pairs which consume low power, but the fault coverage value will be low. So, as a result, we need to apply a large number of patterns, maybe finally we will end up applying more patterns, and as a result the power consumption getting increased. So, we perform a search for a pattern set with low power and high fault coverage with a proper reordering of the set. So, the procedure that I have told, so this definitely gives us the ordering also. So, the order in which the pattern set has to be applied, so that the power consumption is less. Now, this algorithm is a bit directed, like it is starting with the least one, then it is doing something, so that if the next pattern selected is low power one, and that way it is working. Now, we can, so but this problem is an NP hard problem. So, you cannot have any deterministic, there is no known deterministic algorithm that can solve this problem optimally in polynomial time. So, there are several works that talk about genetic algorithm based solution for this problem as well. So, genetic algorithm based solution, so it will select a set of patterns from the set, and after that the ordering will be done using the procedure that I have just discussed. Okay. So, this way it can explore the search space efficiently. To take a typical example how this vector reordering can help in the transition reduction process. Suppose I have got a 3 input circuit with inputs A, B and C, A, B feeding an AND gate, and this is I finally feeding one OR gate. Now, if we are going for an exhaustive test, for example, now a typical example can be that I use some sort of a counter that so mod 8 counter, so that generates all the 8 test patterns exhaustively. So, it starts with 0 0 0, 0 0 1, etc. So, if you just count the values at x and y, so these x values are 0 altogether up to this 1 0 1, and then the next two patterns it is 1, and y is like this. Now, let us see how many transitions have occurred. So, in the x line there is a transition at this point. So, after applying pattern 1 0 1, when we apply the pattern 1 1 0, so there is a transition. So, that is transition count 1, whereas on the y input, so there are transitions like 0 0 0 to 0 0 1. So, there is a transition, this is a transition. Similarly, this is also a transition from 1 to 0, this is also a transition from 0 to 1, this is again a transition from 1 to 0, this is again another transition from 0 to 1. So, on the y line there are 5 transitions, on the x line there is a single transition. So, total number of transitions, if we do an exhaustive testing in this particular sequence, so it is going to be equal to 6. Now, if we can apply that exhaustive test pattern set in a different order. So, not in the monotonically increasing order. So, if we can do it like this 0 followed by 2 followed by 4 then 1 then 3 5 6 and 7. So, how did I come to this ordering? So, this is just by observation. So, what we wanted to do is to minimize the number of transitions in x and y. Now, it may be difficult or it may be easy to generate patterns in this sequence. So, as we know that if we are trying to generate any arbitrary sequence counter, the circuit the pattern generator circuitry, that will become complex, the counter design will become complex, and that counter will also consume some power. So, that is another issue. However, if we can do this thing, then you see the number of transitions could be dropped to 2. So, there is a transition from 0 to 1 here and there is a transition from 0 to 1 here. So, there are only 2 transitions. So, compared to 6 transitions, there are 2 transitions here. So, if you measure the power consumed by this circuit when these patterns are applied in this order, it will be more than the order in which it is applied here. So, in this the power consumed when it is applied in this order. So, this is a small circuit. So, then you see that this reordering of pattern set, it could reduce transitions by some value. So, if it is a large circuit with large number of gates, the number of transitions getting reduced will be significantly more. Now, this analysis is good because I am taking what are the inputs coming to the circuit and primary inputs coming to the circuit, and then we are computing the transitions at each gate. Now, for scan circuit, this cannot be a good approach. Why? For the scan circuit, when I am apart from this primary inputs to the circuit, which I have not shown here explicitly, assuming that primary inputs and primary outputs are also on the scan chain. So, through this scan chain, the test pattern is getting shifted. Now, in each shift, okay, so that will generate some transitions in the circuit. So, if we are looking for an exhaustive calculation, then what we have to do is that if I have to shift in the pattern say 1 1 0 1 0 1 like this, then and initially assuming that the scan chain the scan chain initially contains all 0. Scan chain initially contains all 0. So, if we assume that this flip flops they have been reset and it is containing all 0. Now, first this 1 bit will be shifted into the scan chain. So, it will become 1 0 0 0 0 0, then this 0 will go. So, this 1 will come here and this new 0 will be going to this point. So, you see that this process will continue. So, and there are transitions like this cell I have already seen 2 transitions, this cell I have seen 1 transition, again this way there will be transitions. Now, ideally what is required is that this scan cell output, this scan chain output will be fed to the circuit. So, they are connected to the inputs to the circuit. So, for every transition that occurs, I need to compute the total number of transitions in all these gates. So, I need to do a logic simulation of this circuit for every shift that I do, which is, so this is a very cumbersome thing. So, very complex computation that is that will be required. So, overhead of computation will be very large. So, this is the first observation that a good amount of power is consumed when test patterns and responses are shifted through the scan chain. So, when I am shifting in the pattern, so it will create transitions in these flip flops. As a result, it will see these primary inputs, they will see some transitions here, and as a result this circuit will start consuming power. So, this is a major source of power consumption. Rather than your capture cycle, launch and capture cycle, the shifting process, so that itself consumes lot of power because of this shifting that is occurring through the scan chain. So, ripples that are coming on the scan chain, they cause transitions in the circuit inputs, which in turn creates transitions in the circuit gate. So, this point there are transitions. So, those internal circuit will also transition. So, what is the way out? Way out is we can do some test vector reordering or we can do some scan flip flop reordering. But whatever we do, the major problem that we have is that computational overhead, like we have to do a logic simulation for every scan shift. So, somehow we need to avoid that. So, what is done is we come out with something known as weighted transition metric. So, first of all, it has been there are a lot of studies that tells that if you have a scan circuit where you have got the scan chain here and then it is fed to the circuit, then the power consumed by this circuit is proportional to the transitions that you see at this point. So, if you measure the transitions that are occurring at the input to the circuit, that in many cases is a good estimation of the power consumption of the circuit. And in fact, what we are looking for is we will do some modification to this scan chain. Now, if I modification 1, if I have got two modification schemes, modification 1 and modification 2. So, I do not need the exact power values for modification 1 and modification 2, rather I need a measure by which we can compare between these two modifications, which one will be better. Now, it has been seen that if you compute the transitions that are occurring in the scan chain itself, that is a good estimate. So, in case of modification 1, so if we see that in the scan chain there are more number of transitions than in modification 2, then modification 1 is expected to consume more power. So, it is the circuit under modification 1 of the scan chain is expected to consume more power than the circuit under modification 2. So, we do not need to do explicit logic simulation of the circuit. So, that is not required, logic simulation of the circuit is not required. You can just compute what are the transitions, how many transitions are occurring in this scan chain when I am shifting in the pattern or shifting out the previous response. So, that is what is going to be measured, and that is known as this weighted transition metric. So, in this case, so this is the situation, we have got the circuit under test, and suppose we have got a scan chain consisting of 4 flip flops FF1, 2, 3 and 4. So, scan input is connected to flip flop 1 and scan output is connected from flip flop 4. Suppose we have got these test vectors V1, V2 and V3, V1 is 0 1 0 1, V2 is 1 0 0 1, V3 is 0 1 1 0. And on the other hand, this response is like this, when we apply V1, so response is 0 0 1 1, that is R1, R2 is the response of V2 and R3 is the response of V3. Now, what happens, like I have got 4 cells, and so this one. So, first if you look into the scan chain values, so when I am shifting in this 0 1 0 1, first that 0 goes. So, initially all the flip flops were 0, now 0 comes. So, 0 it remains 0 0 0 0, first 0 has got shifted, then the next 1 gets shifted. So, 1 comes here, 0 goes there and this remains like this, then another 0 comes. So, 0 comes here and this 1 goes here 0 0. So, this way actually this transition will be taking place, then this 1 0 1 0. Okay, so, it will go like this. Now, you see that there are in the original test vector was so original test vector was 0 1 0 1, original test vector was 0 1 0 1. Now, you see that this particular transition, so this 0 to 1 transition, so this has this has gone to how many places? So, this has affected this cell, this has affected this cell. So, 3 cells have got affected, whereas the next one that we had, so this 1 to 0 transition, this one, so this one has come to only this transition has got affected. This 1 to 0 transition, it could not go to the next position. So, because of the length of the scan chain. Similarly, this 0 to 1 transition, so it could not go anymore. Okay. So, if I have got a pattern like this 0 1 0 1, you see that in the pattern there are some transitions, but from 0 it is going to 1, then it is going to 0, then again to 1, but they do not have the same effect on the scan transitions. Like this 0 to 1 transition, so it will affect 3 flip flops, this 1 to 0 transition will affect 2 flip flops, and this 0 to 1 transition will affect only 1 flip flop. So, in this way can see that these scan transitions, so they do not go to all the flip flops. So, accordingly we can define something called position of transition. So, this is this is this position, if there is a transition, so we call it position 1. So, between any two bits we call it position. So, it is position 1, this is position 2, this is position 3. So, for the first V1 we have got transition at position 1, position 2 and position 3, all the 3 positions. Now, number of transition, so weighted transition is computed as size of scan chain minus position of transition. So, you see that if this is the test pattern that we are going to shift, this transition is occurring at position 1. So, but when it is occurring at position 1, so this will be affecting all the 3 flip flops, So, that is so this weighted transition is computed at size of scan chain minus position of transition. So, 4 minus 1 equal to 3. If there are more number of 1s here, then of course, that those will be added, those transitions will also be added. In fact, in the previous example that we were considering, so this is our position 1, there is a transition. So, it is 4 minus 1 3 plus position 3, there is a transition 4 minus 3, that is 1. So, total there will be 4 transitions that will occur in the entire scan chain. So, in the shifting of this pattern. So, that way we can have this weighted transition metric computed. On the other hand, for the output response, that is not the case. So, output response, so the positions are marked from the other side. So, this is if I mark it from position 1 to position 3, now this bit will be going out immediately. So, this transition from 1 to 0, so this can affect only the last flip flop, whereas if there is a transition at this point, so it will affect all the 3 flip flops. Okay. So, that way position will be has to be counted from other side, and then this is captured by this formula, again by the same formula, the size of scan chain minus position of transition, but the position is taken from the other side. So, it is from the output side, from the input side, from the flip flop one side is position 1, and that way it goes. So, this way for this entire set of test vectors and responses, so we can compute this weighted transition for each of the pattern, test pattern and the response, and those values can be added to get the weighted transition metric.